All right, before we get started, Minneapolis, Minnesota. Anybody who lives there or anybody with the wherewithal to get themselves to the Twin Cities, you guys listen up. Anybody else, just hit skip 30 seconds twice. I'm going to be at Farcon 2017, and that's August 23rd and 24th. I'm telling you right now because you got to go get tickets. The conference is free of charge thanks to the sponsors. You got to get over to farcon2017.eventbrite.com to pick yours up. That's going to be in the show notes as well. Tickets just became available, so if you're listening to this on Friday, the day of release, you got a good shot at getting a ticket. We'll follow up down the line with a few announcements about what's going to be going on there. Trust me, it's going to be worth your while. You can read all about it on their website. If you're in Minneapolis or you can get yourself there, go pick up a ticket. Like I said, these are going to move fast because it's free and it's a great event, good lineup. If you're hearing this late and you want to go and it's sold out, maybe come talk to me. I'll see if we can sneak somebody in the back or something. Maybe there's some extra tickets I can squeeze out of them. Get on Slack, DM me, we'll talk about it. But try and go over there and get registered if you can. Farcon2017.eventbrite.com.
Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Marwa Mahmoud received her PhD in computer science at the University of Cambridge, England in 2015. She is currently a postdoctoral researcher in the Graphics and Interaction Group at the University of Cambridge Computer Laboratory, where she studies emotional inference from gestures and expressions. Marwa's research interests lie in the field of effective computing, social signal processing, and automating machine understanding of emotional body language. Aspects of her research draw on computer vision, machine learning, human-computer interaction, and psychology. Marwa holds a BS and an MS in computer science from the American University in Cairo, Egypt. Marwa, welcome to Data Skeptic.
Welcome. Hi, Kai.
So I've been enjoying reading through a lot of your research paper. You do some interesting work that I was not previously deeply familiar with, and I came across one particular paper I wanted to talk to you about, estimating sheep pain with facial recognition. So the title sort of tells it all, but I'd love to hear your background on what got you interested in conducting a study like this.
So this work started by when my group, my supervisor, Peter Robinson, he got approached by the vet school here in Cambridge, where they were wondering if we can apply the face analysis techniques we use on humans, on sheep. The main contact was actually Krista McLennan, who developed a scoring system that maps specific changes in the facial features of the sheep and map these changes to a score, a pain level score. And the main idea, or why this was used mainly, is for early detection of some painful diseases in sheep. So this pain level scale is used to detect if the sheep is in pain. And since it's based on specific changes in a facial feature, and this is summed up, and then and then a threshold is applied to decide if the sheep is on pain or not. So because there is this scoring system, when we talked, we thought it's a good idea to really apply same techniques used for human facial expressions and detection of action units on sheep. This is how the project started.
What does a sheep look like when it's in pain? Or how does it look different from its normal face?
So the ear flipped is a sign of pain. Mm-hmm. The V-shaped nostril is a sign of pain. Also the eyes, they also have these sort of partially closed eyes rather than wide open eyes. So they have so it's really specific features on the face. It seems to me that's similar to sort of human just being like have this tense face, but it's not very similar. I mean, we don't move our ears when we are in pain, right?
Sure.
But yeah, well, there are actually clear signs of pain that appear on the sheep face.
Can you tell me a little bit about how you get your ground truth measurement of whether or not they're experiencing pain?
Well, we get all the ground truth from vets. So we work with Krista McLennan, and she's in the vet school. She used to work here in Cambridge. Now she's a lecturer at University of Chester. She works with us on labeling the photos of sheep, both labeling of the action units, so labeling on different facial features, and label of the final score. And this is how we get the ground truth. Currently, the data set as well was collected in the same way. So we get all our data from vets. That's one of the challenges as well, because we need more data, but this needs lots of work from vets and from us to do the labeling.
Must be a very expensive and time-consuming process to build up a corpus. Is there, in the human facial recognition world, there's some stuff you can get access to online. Are there any resources available that can help you in a project like this, or do you have to create your entire corpus?
No publicly available stuff. But actually, in creating our corpus, we used faces that were collected from the farm, and we augmented our data set as well by just like Googling sheep faces. So there are plenty of photos on Google of sheep, but then still labeling is needed. So that still doesn't help much. Challenges also arise because you can't ask a sheep to pose. So all the photos will include lots of like background, sometimes many sheep at once, sometimes lots of other animals, pose of the face, different viewpoints. To start research on that, you need to start with like a clean database to start applying your techniques. So that was a little bit difficult as well to start with. So we excluded lots of images that had maybe different breeds, because if you don't have enough data for example, sheep with like black faces or half and half or something, then it's better to exclude the whole breeds. Otherwise, you won't get enough results. So we hope to extend this work to be applied for other breeds, but again, this needs data.
Yeah, makes sense.
Which is very similar to human, actually. I mean, the human facial expression analysis. The more data, more variation, this means better systems, better classification systems.
Yeah, definitely. More data, or better data, maybe not so much better algorithms are the key.
Exactly. That's correct.
So you've got these veterinarians who fortunately know how to recognize the pain and they can contribute your labels. Of course, that's a specialized skill and not anyone can do it, so it makes getting those labels hard. But I was also curious, is there a threshold to their accuracy? I have a pet parrot, and I feel like I understand her too a bit, but not even perfectly, because I'm not attuned to perceiving her pain per se. How accurate do the human scorers think they get in their labels?
This is a good point, because when we look at the labels for the specific action units that we get from the vets, sometimes it's not very clear. For example, let's take the ear shape, for example. So it's very difficult to differentiate between like different rotations. So maybe clear ear flat would be very different than ear flipped, but the middle stages might be a little bit tricky. And we use these labels in our training, but that's why when we looked at like the false positives, or why we can get where is the error, for example, the error percentage happen, we noticed that this is because some of the labels might really, some two shapes might look very similar from like a human eye, but you're still not sure how these were actually labeled by the vets. So maybe the vets as well don't use only these different, they know, somehow maybe they know how the combined features would mean, so they would know if the sheep is on pain or not. So I'm not sure exactly how reliable the labeling of the action units that we get from human labelers would be, but I guess if we can have ground truth at some point, if we have more data, and also maybe get ground truth on if the sheep is actually sick or not, so maybe this can be a better ground truth, in my opinion, instead of having label for every action unit, what I call action unit, which is the difference in different face regions. Maybe if we have just one score that's a ground truth, an actual ground truth that says how sick is this animal, then we can maybe train better systems that can jump directly from the face to the pain score or the diagnosis.
Would you mind defining that term you use, an action unit?
Action units comes basically from the facial action coding system, the FACS, that was actually developed by Ekman. It's a systematic way of defining different changes in the facial expressions of human based on the muscle activation. So different action units means different changes in the face. So for example, there's an action unit for a smile, there's an action unit for the eyebrow raise, action unit of eye open, eye closed, and so on. So it's a coding system for the facial movement. This is developed for humans, and here we just use the same terminology. There isn't really an action unit system that's developed for sheep, but I guess from seeing how vets actually mark every facial feature and have a specific score that's actually correlated with every facial feature, so it looks very similar to the human action units.
Getting back again to the corpus, can you tell me, roughly speaking, how many labeled images you had to work with?
So we had around 500 images.
Mm-hmm.
So these were the labels we've got. So for different stages in our work, because we start, for example, by face detection, and for that we did some augmentation for the data. So we cropped the faces and tried to put it on different backgrounds just to augment the data a little bit and add more. So we reached about 5,000 for the face detection bit. But yeah, the amount of data we're working with are only 500 labeled images.
And we know we've already discussed the cost of growing that, so you don't have the luxury that some researchers have with, ImageNet and MNIST and really large databases like that. So I imagine you have to do some of the pre-processing you discussed, but also a fair amount of feature engineering as well.
The first step was the face detection, but later on in detection of the taxonomy. So what the features we used are appearance features. We use histograms of oriented gradients, and we use this around the detected facial points. So we define a set of boxes, for example, for the ear, for the eyes, and then we detect hogs out of these features, and these are then classified using an SVM. We also explored, because of the data and the limited amount of data, we did some exploration with doing binary classification rather than a three-way classifier. This improved a little bit the performance. Also, this helped in excluding the middle stages. For example, as I mentioned, the ear difference. So, for example, intermediate stages are not that clear as in the extreme cases. So we did some of that as well. Another thing as well, because of the limited data, we excluded the profile faces. So we just used front sheep with frontal faces. Again, because we don't have enough. If we don't have enough of a specific category, so it's better to exclude it for now. And that meant as well excluding some features such as changes in the cheek. So I didn't mention actually what are the features that are important are mainly ears, the nostrils, and the eyes. And there's also the cheeks, but we excluded this bit for the work so far because we don't have profile faces of sheep. But actually there are even more action units or more features that can be added if we have more data. And that's actually the plan. So this summer, we're still going to extend the work on that. And we're hoping to get some more data that would include some profile faces. Not necessarily for the same sheep, for the same animal, but maybe for just different animals. And this might actually mean extending the taxonomy as well to include more features.
So when you've got all your features and then you go train your SVM, can you tell me a little bit more about those labels exactly? I know they're a measurement of pain, but is it a regression problem, like a score, or do you treat it like a categorical problem where there's a few categories of pain? What are you trying to learn?
So there are two scenarios, and they are both based on the data that we've got. The data that we've got had a label for every feature. So for example, if the ear is flat or not, for every action unit, we get a label for its presence. So for example, U-shaped nose, yes or no. So it's a categorization problem, it's a classification. And that's for every action unit. So for the 3 action units of the ear, either it's flat, slightly rotated, or totally flipped. These are 3 action units. So we just get a tick, which one of these is present in this photo. Nostrils, for example, if it's U-shaped or slightly V-shaped or very extreme V-shaped, and so on. Because the data we've got is based on the action units, so this is the way we done it in this work. We treated the problem as a classification problem for every action unit. So we trained an SVM for every action unit just to detect the presence. So it's a binary problem for every action unit. We tried as well another technique which used an SVM for every feature. So this means it's a 3-way classification. So for every feature, so for example, the ear, we decide which action unit is present. Is it ear flat, ear slightly rotated, or ear flipped? And this would be a 3-way classification problem, which is slightly harder because then you would include lots of the intermediate stages that are not very well labeled. It's ambiguous. So the intermediate steps can be a little bit ambiguous. We experimented with these, and then at the end, we deduced the pain score from the result that we get from these separate classification, these 5 classification SVMs.
Why was support vector machine the right choice to use here?
I think mainly because of the amount of data. So I think for the amount of data, we couldn't be using like deep learning or something that's more sophisticated because we need more data for that. So SVMs are simple in terms of the number of parameters that you need to tune. So for this amount of data, this would be the best choice we have. And it worked, I think, quite good given that we don't have enough training samples.
Yeah, what sort of accuracy did you guys see?
The most challenging experiment, which means like doing this 3-way classification for every feature, we reached a 67% classification rate, which is like fair enough given the amount of data we've got and the amount of ambiguity of the intermediate stages. But this actually was boosted to like about 80% or so if we exclude the intermediate stages and treating the problem as binary, treating every feature as a binary classification rather than, so this means really excluding a bit of the ambiguous intermediate stages.
What do you think is keeping it from being higher? Is it just more data, or are there techniques, or could it even be that certain animals are trying to hide their pain? Does that play into the limited degree to which you can get accuracy on this?
I guess animals don't hide their pain that much.
No? Oh.
Well, maybe. I don't know. We need to...
Maybe I'm anthropomorphizing, I guess.
Yeah. Well, I guess there are many reasons. One reason is, we've tried to clean the data and have as sort of clear images as possible. But again, given the examples, I don't know if you've seen the sample images from the data set in the paper, but there's still lots of like different sort of faces, different colors, a little bit of difference in the color. We did clean the data, so we excluded the ones that look totally different, but still there are lots of variation. There is also lots of variation in the viewpoint as well in these images. So I think better data will definitely improve accuracy. Also, as well, there is a possibility of actually excluding the whole step of detection of the action units. So maybe we just map directly from the face, from the appearance features to the pain level. We haven't tried that yet, but I think this can improve also the accuracy. That's actually the next experiment that we're planning to go ahead with doing, because then you would actually depend on the classification system or the SVM to build the model, like a holistic model. It could be that actually detection of the action units means accumulating some of the errors in the labeling of the of a specific action units. That's how I'm thinking about it. So I think if we exclude the intermediate step and maybe map directly from the sheep face to the pain level, we can get better results.
So when I read the paper, by the way, I'll have a link to the paper in the show notes, and I encourage everyone to check it out and see the images and, read into the more details. I kind of presume that, I guess, some of those intermediaries, the, extracting facial action units and the histogram of oriented gradients that we haven't gone into yet, that those were essentially useful techniques you developed in a sense to compensate for the limited corpus of data. You couldn't go to deep learning with just 500 images. So rather than hoping deep learning would do your feature extraction for you, you brought your knowledge of the field and the species and that sort of thing to the table to extract those features and then give it the ability to learn on a more limited data set. So are you going to be able to go more directly from the image just by better technique, or will that demand a lot more images?
Well, definitely, if we have more images, we'll have better techniques, as we mentioned at the very beginning. But we need to experiment with that. The reason why we used also these sort of action units, because the scoring system that we got from our vet collaborators was still based on specific scoring for every feature. That was one of the reasons we start with that. The experiment I'm thinking about is actually if we still use appearance features, again, still use appearance around specific features, so not really feeding completely raw data. No, again, still apply some feature extraction that can be hogs or maybe some geometric features as well on the specific landmarks. So around specific landmarks and again around specific features, and then map this directly to the pain level. What I'm hoping to achieve by doing this is to really just compensate for any bias in the labeling of the specific action units. I think that's especially for the intermediate stages, because as I told you, when we, for example, excluded the intermediate action units or the intermediate changes of the shapes, we got better results, because basically maybe just like a totally clear ear flat is totally different than ear flipped, and that was very clear in the appearance. It was picked in the appearance features that we extracted. That's what I was hoping to do. But definitely, I mean, it's still very difficult to go to something like deep learning with this amount of data.
Today's episode is sponsored by Periscope Data. Periscope Data is a web-based tool for database exploration, rapid visualization, and dashboard development. I like it because of how accessible it makes my data to me. No longer do I have to write a query, then write some matplotlib code or some ggplot. One-step discovery makes things happen a lot faster. It connects to all the major database types and even joins across them. It's perfect for teams. You can get the ad hoc query monkey off your back if you find yourself bombarded with constant requests from your colleagues. Do that by building the perfect chart. Do it once, make a dashboard out of it, and even set up that dashboard to automatically email it to the right people every day. Never make that same report twice again. If you believe in reproducible analysis, head over to periscopedata.com/skeptics to check it out. Once again, that's periscopedata.com/skeptics. So how well will these techniques transfer to other animals?
I think all of them are transferable to other animals, given that we have the data and do the proper facial landmark detection, because the landmarks will definitely. So retraining all of the facial landmark detection systems and doing the feature normalization based on the animal that we're handling. But it should be easy to map the facial feature analysis to other animals as well. And given as well that we have the scoring system, that we need definitely the work of vets on that, because we don't have the knowledge of how different species express pain.
In certain cases, transfer learning has been celebrated as a useful technique in image recognition. I think a lot of the use cases I've seen are maybe very close to the original. So maybe someone has a neural network that was trained on ImageNet to recognize let's say, certain types of tools, and then someone could extend that to recognize the brand of the tool. And this is sort of they benefit from the early training and the way the network was essentially initialized. Do you think that there's an opportunity there for you to benefit from transfer learning, or is what we've learned about human faces a little bit too foreign to transfer cleanly to your domain?
There's some work done, actually. I've seen a recent paper at CVPR that at the work done by a group in UC Davis, they did use a little bit something similar by actually warping the face of the animal to look a little bit similar to how the human face looked like, and then use transfer learning for the facial landmark detection. The paper reports very good results, but my sort of concern with that is that we have different features on the face of the animal that are important. So which parts of the face are the most important parts? So for example, the ear. When we look at the facial landmark detection of human, we do not detect the ear. The ears are totally excluded.
Yeah.
So while actually the ears are the ear is one of the very important and clear feature that actually where it shows different sort of emotions or pain in many animals, not only sheep. So that would be the tricky part. So yeah, I guess the regions of interest in the sheep or in different animals might be different than in human. As well, something like also how to do the normalization, what are the static points so for example, human nose usually is used in some of the tips of the eye because these don't move. So how this maps to other animals. We need to be a little bit cautious with this, but nothing in my mind so far. I'm not sure how we can use transfer learning to do, but definitely worth exploring maybe.
So it seems to me that the animal rights community ought to be big fans of your research. It's not at all invasive, and the more successful you get, that provides them a tool for maybe, helping those animals to communicate in a way they weren't able to before. Have you seen that sort of response?
Well, there's lots of interest from animal welfare, definitely. Having an automatic way to assess the pain or the difference will definitely help early detection as well of specific diseases, and it is non-invasive. Yes, there's plenty of interest, mostly from the animal welfare people, but not sure. I think the media is the one that picked this up.
Makes sense. Can you talk about some, obviously it's a research project, but do you aspire to any industrial applications, or where do you see the work ultimately contributing?
We're trying to move this a little bit again under the sort of the research umbrella. Not sure about industrial applications, but no, we haven't heard from any sort of industrial collaborators. It's mostly universities here in the UK, so yeah.
So what's next in this line of work? What kind of things are you continuing to pursue beyond what we've had a chance to read about in the paper?
We're working still on sheep, and that's mainly because of our vet collaborators and the data that we can get access to. So next step is to work on profile faces and extend the taxonomy to include maybe other features such as the cheek, and improving the technique as well so that we can get better analysis of the pain. That's what I mentioned, is that if we can just go directly from the face to the pain score, this might a little bit increase the accuracy. Given that as well, that also that the pains, the labels that we get is just from one person as well. So I think also there are lots of probability of having some bias in the labeling.
Where can people follow your research and future things like this online and maybe keep in touch if they want to?
Yeah, sure. So we have actually a web page for the project under our group, the Graphics and Interaction group here in the lab. If you just go to the website of the University of Cambridge under the Graphics and Interaction group, you can reach this by just www.cl.can.ac.uk/emotions. And here we have all the list of projects that we're working on, and this include ovine affect. We have like a sort of a summary of what we're doing so far and list of applications that hopefully we're working on.
Very cool. Well, I'll have a link to that in the show notes so people can follow up. Marwa, I want to thank you so much for coming on the show and sharing your research. I think it's a really interesting thing, not only for its value in the sort of biological sense, but a nice example of machine learning in an applied way. So I was very grateful to get a chance to speak with you.
Thank you so much, Kyle. It was nice speaking with you as well.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.